welcome to my speed run presentation for Edexcel GCSE Combined Science Physics Paper 5. This goes through all the content quickly and is intended as a bit of last minute revision just before the exam and should not be the main bit of your revision. Starting with topic 1, motion. It covers vectors and scalars, velocity and distance time graphs, acceleration and velocity time graphs. So vector and scalar quantities. Scalar quantities are quantities that only have size, for example, mass, distance, and speed. Vector quantities have both a size and a direction, and for example, weight, displacement, velocity, acceleration, and forces. We can draw these with arrows, with the length of the arrow representing the size, and the direction of the arrow, the direction. Speed and velocity. So speed is how fast you are travelling in units of meters per second. Velocity is how fast you're travelling in a certain direction. So going around the roundabout here, the speed is constant, but the velocity is changing because the direction is changing. You calculate velocity and speed according to this equation. Speed or velocity equals distance divided by time. Make sure your distance is in meters, your time is in seconds. And we've got this equation triangle here, and the symbol version of the equation v equals x over t. Distance time graphs describe how the distance changes during a journey. So we have time on the x-axis, distance on the y-axis. When the graph is sloping up, you're moving away at a constant speed. When it is horizontal, you're stationary. And when it is sloping down, you're moving back towards your starting point. To calculate the speed, we need to find the gradient of the graph. So to calculate the speed in section B here, we calculate the gradient. So we're going to do the speed, which is the height here. So that is 15 up to 20 is 5 meters per second. Divided by the time. So from 5 to 15 is 10 seconds. So our speed is going to equal 5 divided by 10 equals 0.5 meters per second. Acceleration is changing velocity. Velocity is a vector quantity. So you're accelerating either when you're changing speed or when you're changing direction. So if we look at the roundabout here, although they might be traveling at a constant speed, they're still accelerating because their direction is changing the whole time. If acceleration is positive, that means you're speeding up. If acceleration is negative, it means you're slowing down. Acceleration is measured in units of meters per second squared, m/s to the power 2. Acceleration is calculated as acceleration equals change in speed divided by time. Speed is in meters per second, time is in seconds. We can alternatively write that as a equals v minus u over t, where v is your final speed and u is your initial speed. A velocity time graph shows how the velocity changes during the course of a journey, and we have the time on the x-axis and the speed or velocity on the y-axis. This time, when the line is sloping up, it means you're accelerating, you're speeding up. When the line is horizontal, it means you are coasting at a constant speed. When the line is sloping down, it means you're decelerating, you're slowing down. When the line is on the x-axis itself, that is when you're stationary. Now, two sets of calculations we need to do here. First thing is we need to be able to calculate the acceleration. So to do that, we do a change in speed divided by time. So to go from B to C, our change in speed is going from 10 down to 0, so that is minus 10. And our time is going from 10 to 13, which is 3 seconds. So acceleration is going to be minus 10 divided by 3 equals minus 3.33 meters per second squared. We also need to be able to calculate the distance that we've travelled in any given section. So for example, going from E to F, the distance travelled is the area under the graph. So we're going to find out the area of that rectangle there. Now the area of a rectangle is base times height. So the base going from E to F is going from 21 to 25, which is 4. And the height of it is here, so we see that is 5. So the area, so the total distance is the area, so that is 4 times 5, which equals 20. Sometimes you have to do it for triangles. Remember, the area of a triangle is half base times height. Topic 2, forces and motion, in which we look at forces, Newton's laws of motion, and momentum. A force is a push or a pull. Forces are needed to make things start moving or make things stop moving, but they are not needed to keep them moving. Forces are vector quantities with both a size and a direction, so we can represent them using arrows. The units are newtons, and they can be measured using a Newton meter, which has a spring that pulls down the more the force is applied. Some common forces, we've got normal force, normal reaction force, thrust, weight, friction, air resistance, and upthrust. Objects often have many forces on them, so we draw diagrams like this called free body diagrams, showing all those different forces. Resultant force is the force remaining on an object when forces acting in opposite directions are cancelled out. So we looked at these three body diagrams, we've got these forces acting in many different directions, they all add up to one overall force. And this is important because objects only accelerate when there is a resultant force, they stay at a constant speed if there is no resultant force. In this example here, the 5 newtons right and the 5 newtons left cancel out just to leave you with the 5 newtons down. There can be more complicated examples like this one here. We've got 5 newtons right and 3 newtons left. That gets completely cancelled out and we end up with just 2 newtons going right because 5 minus 3 is 2. And we've also got 2 newtons going up. Those combine together to make a diagonal force sort of going in that direction. Newton's first law of motion tells us that an object will move at the same speed and direction unless it experiences a resultant force. This tells us that objects speed up when they experience a resultant force or they slow down. But if there's no resultant force, they will stay at the same speed. This is counterintuitive. So on the motorway, for example, if the car is cruising at 50 miles per hour, there is no resultant force. The engine may be making 500 newtons of forwards force, but that is being balanced out by 500 newtons of friction and air resistance, meaning the overall resultant force is still 0. Mass versus weight. Mass is a scalar quantity, and it is the amount of matter in an object and is measured in kilograms. Weight is a vector quantity, and it is the force of gravity pulling down on the mass of an object, and because it's a force, it's measured in newtons. Your mass stays the same wherever you are, so this astronaut has a mass of 120 kilograms regardless of whether they're on Earth or on the moon. However, because gravity is stronger in different places, it's strong on Earth, so this astronaut's weight is greater on Earth because gravity is stronger, and lower on the moon because gravity is weaker. Weight is calculated using this equation here, so weight equals mass times gravitational field strength, with mass being in kilograms. On Earth, we need to know that the gravitational field strength is 10 newtons per kilogram. Newton's second law of motion tells us that force equals mass times acceleration, F equals m times a. Units are newtons of force, kilograms of mass, meters per second squared. For acceleration, we get this equation there. I think this is better though written as acceleration equals force divided by mass, because what this tells us is that if we have a greater force, it gives us a greater acceleration. If we have a greater mass, it gives us a lower acceleration, because if we're dividing a force by a bigger mass, we get a smaller acceleration. We investigated acceleration using a trolley that was being pulled along by some weights attached to a string over a pulley, and it was passing through some light gates, and the light gates measured the acceleration. So we set up the trolley with some masses and a string and some light gates. We placed a 10-gram mass on the mass hanger here, and we released the trolley and measured the acceleration using the light gates. Then we transferred another 10 grams from the trolley onto the mass hanger and repeated the experiment. We did this up until about 100 grams of mass had been transferred in total. Then we produced a graph of the acceleration versus the force, and we should have found, if we did it properly, that we've got a line that was directly proportional, so that's a straight line that passes through 0. Newton's third law of motion tells us that for every action force, there's an equal but opposite reaction force. This tells us that if I push on a wall with an action force, the wall pushes back with a reaction force in the opposite direction. If you think about a balloon that you've blown up with air and let go, the balloon pushes down on the air with an action force. The air pushes back up on the balloon with a reaction force, and it is that force of the air that is actually what pushes the balloon along when it's flying around. Momentum is the tendency of an object to keep moving, and it is calculated using this equation. So momentum equals the mass times the velocity. The units for momentum are kilogram meters per second. For mass, it's kilograms, and for velocity, it's meters per second. Now, momentum is a vector quantity, so the direction matters as well as the size. And there's an important idea called conservation momentum, which tells us that the total momentum before and after a collision is the same. So when these two people here push off each other, their momentum in each direction needs to be the same, so that the total momentum adds up to 0, and so they will go off at the same speed. Okay, when a big person and a little person push off against each other, the big person will end up moving slowly and the little person very quickly, because a small velocity times by a big mass will have the same overall value as a large velocity times by a small mass for the woman. Momentum is increased or decreased by forces. So force is the change in momentum divided by time. We get this equation here, mv minus mu over t. V is the final velocity, u is the initial velocity. and m is just the mass. Stopping distance is the distance a car travels from when the driver first spots a hazard to when they reach a complete stop. It is made up of thinking distance, which is the distance travelled whilst reacting, which is affected by your speed, and by your reaction time. Your reaction times are increased by your age, drugs, tiredness, distractions, and illness. And it's also affected by your braking distance. Your braking distance is affected by your speed, the condition of your brakes, the condition of your tyres, and the road conditions. Braking distance is how far you travel whilst you're braking. Crashes are dangerous because they create large forces which can injure people. So to improve car safety, we take advantage of this equation here, force equals change in momentum divided by time. If we can increase the time, we decrease the force, which makes cars safer. So we can increase the time a collision takes by using crumple zones, which crumple up, by using airbags, which give way when our head hits them, and using seat belts, which stretch slightly during an accident. Topic 3 is about energy. It covers types of energy, energy transfers, energy efficiency, and energy resources. So energy is measured in units called joules, written as a capital J. There are stores of energy: kinetic, which is movement; thermal, which is heat; gravitational potential; elastic potential; chemical; and nuclear. Other forms of energy include light, sound, and electrical. Now, energy is always conserved. It cannot be created or destroyed, just changed from one form to another. And those changes are called energy transfers, in which we say where energy goes from and to. So, for example, the energy transfer in this light bulb is from electrical to light. Energy efficiency tells us how much of the energy we put into something is converted into the useful energy we want out of it, and it is just the useful energy out divided by the total energy in. It gives us a number between 1 and 0, 1 being the best and 0 being the worst. We can never reach an efficiency of 1 due to the idea of dissipation, which tells us that energy tends to spread out, so we always get energy converting into multiple different forms anytime there's an energy transfer. And we can show that using a Sankey diagram, where the thickness of the arrow represents the amount of energy. So in this case, 100 joules of electrical energy makes 10 joules of light and 90 joules of heat. The arrow here is thin because 10 joules is much less than 90 joules. Heat is transferred in 3 ways. First of all, by conduction. Conduction involves hot particles vibrating and knocking into their neighbours and making them vibrate, and you just have this wave of vibrations travelling throughout the material. Convection is the idea that hot liquid or hot air is less dense, and so it rises, and that moves heat from down low to up high, and the hot air then cools down as it rises and sinks again, and that ends up creating these currents of hot air rising and then cooling and then rising and then cooling and so on. And then finally there's radiation, which is heat given out in the form of infrared, and when it is absorbed by materials, it makes the particles vibrate, which heats them up. So, stored energy. Gravitational potential energy is energy stored in objects based on their height, and the change in gravitational and potential energy, so delta GPE, equals the mass in kilograms times by the gravitational field strength times by the change in height. So delta G equals m times G times delta H. Remember that delta sign means change. Remember also the gravitational field strength on Earth is 10 newtons per kilogram. Kinetic energy is energy stored in moving objects. So kinetic energy equals half times the mass times the velocity squared. Mass must be in kilograms, the velocity must be in meters per second. So KE equals half times m times v squared. We get energy from renewable and non-renewable resources. Non-renewable ones will run out, and they include oil, coal, and gas, which together are called the fossil fuels, and there's also nuclear energy as well. These all have the disadvantage that they'll run out. The fossil fuels have the other disadvantage that they produce carbon dioxide, which is contributing to global warming, which is leading to global climate change. Renewable energy resources will not run out, and they include many things. We've got wind farms here, we've got solar, this is hydroelectric, this is a tidal barrage, this is tidal energy, and this is biogas. They all have the same advantage that they won't run out. Most of them have a similar advantage that they don't produce carbon dioxide. A lot of them have similar disadvantages, like, for example, these guys, they don't work if it's not windy or if it's not sunny. These two ones, they tend to damage large areas of habitat and so on. They all also have the disadvantage of generally being quite expensive, although the cost is coming down every year. Topic 4 on waves is about describing waves, wave speed and refraction. So waves transfer energy without transferring matter. There are 2 types of wave, transverse ones and longitudinal ones. Transverse ones, the particles vibrate perpendicular to the direction of energy movement, say perpendicular, not up and down. Longitudinal waves, the particles vibrate parallel to the direction of energy movement. Note that in the longitudinal ones, the particles are not moving along. It just looks like they are. The red spots will never leave those red circles. The anatomy of a wave. So we talk about the frequency of waves. That is the number of waves per second measured in hertz. 1 hertz is 1 wave per second. We talk about the wavelength, which is the distance in meters from the top of one wave to the top of the next. The period of a wave is the time it takes for a single wave to pass, and the amplitude of a wave is the height from the middle of the wave to the top or to the bottom, but it is not the total combined height. The speed of a wave can be calculated using two different equations. Wave speed in meters per second could equal distance divided by time, or wave speed could equal frequency times wavelength. Which equation you use just depends on the data you're given. If you're given distance and time, use this equation. If you're given frequency and wavelength, use this equation. The core practical in waves looked at waves in water and two different ways to measure their speed. So we set up a ripple tank, which is here. We shone a light down through it, and we saw shadows on the piece of paper below it. And first of all, we counted the number of waves in 10 seconds, and we divided that number by 10 to find the overall frequency. We then used a ruler to estimate the wavelength of the waves, and we used wave speed equals frequency times wavelength to find the speed that way. We also measured a 30 centimeter distance, and we timed with a timer how long it took the wave to travel 30 centimeters, and we did distance divided by time as a second way to get the speed. We also looked at the waves in an iron bar. So we had an iron bar suspended from a rubber band, and we struck it with a piece of metal to make a ringing note, and the wavelength of that wave is just double the length of the iron bar. Don't ask why. And we measure the frequency of the wavelength with a tablet app, and so to calculate the speed we just did wavelength times by frequency. Refraction tells us that waves change direction when they enter a new medium, and this happens because they change speed. So in general, when a wave enters a slower medium, it bends towards the normal. So the normal is a line drawn at 90 degrees to where the light entered the new medium, and that angle, the angle of incidence between the incident ray and the normal, is lower, so it is greater than the angle between the refracted ray and the normal because light has slowed down. We investigated refraction by setting up a ray box, and we put it on a piece of paper with the glass blocks. We drew around the glass block, and we shone a ray of light through that. We put some little cross marks on the paper to mark where the ray of light had been, and then we drew that in properly to make a diagram. We then added in some normals, like is shown in this diagram here, and we measured that angle and that angle, the angle of incidence and refraction there, and we did the same here. And what we did then was we repeated the experiment with a ray of light shining at a number of different angles, and we did a graph graphing the angle of incidence and the angle of refraction, and we found that the greater the angle of incidence, the greater the angle of refraction. Topic 5 is on light and the electromagnetic spectrum. So when you think electromagnetic waves, think light waves, although we can't see them all. It's the same basic thing. They are all transverse waves. They do not need a medium to travel through, and they all travel in a vacuum at the speed of light, which is 300 million meters per second. And we discovered infrared waves by a very clever experiment done by William Herschel, in which he separated light into a range of different colours using a spectrum. He measured the temperature of each of the different colours, and he found that the hottest one was red, but then an even hotter thermometer was found next to red in the space where it was black, which showed that there was an invisible type of radiation that was heating that thermometer. The electromagnetic spectrum tells us the full range of types of radiation, and that is radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays, and we can remember them in order with the acronym. Rubbish memories include visiting your ex-girlfriend, so R, M, I, V, U, X and G. So rubbish memories include visiting your ex-girlfriend, and that is in order from longest to shortest wavelength, lowest to highest frequency, lowest to highest energy, and least to most damaging. Radio waves are used for communications, and they are not at all dangerous. Microwaves are used for communications, mobiles and satellites, and used for cooking food because they make water vibrate. They have a potential to cause subsurface burns. Infrared is used for short distance communications like TV remotes. It is also used for cooking food, so in toasters and grills, and for infrared security cameras. It can cause skin burns. Visible light is used for illumination and photography. There are no dangers. Ultraviolet is used for fluorescent security inks that glow under ultraviolet light, and for water sterilisation. It can potentially lead to sunburn. It can cause DNA damage that can lead to skin cancer. X-rays are used for hospital X-ray scanners and for baggage scanners at airports. X-rays can cause DNA damage and again lead to cancer. And finally, gamma rays are used for detecting and treating cancer and for sterilising medical instruments in the hospital and also for sterilising food. They again can damage DNA and can cause cancer. Topic 6, radioactivity, covers atomic structure, types of radiation, background radiation, half-life and safety. Atoms are made of protons, neutrons and electrons. Protons have a mass of 1, a charge of +1. They're found in the nucleus and the number is given by the atomic number. Neutrons have a mass of 1 and a charge of 0. They're also found in the nucleus and the number is given by the atomic mass. Take away the atomic number. And finally, the electrons got a mass of 1 over 1835, a charge of -1, and they're found in shells around the nucleus and their number is given by the atomic number. We know that atoms are mostly empty space due to Rutherford's experiment in which he fired alpha particles at some gold leaf and he found that most of the particles went through, which must be because most of an atom is made of empty space. Isotopes are atoms with the same atomic number but different atomic mass. So, for example, carbon has 3 isotopes, carbon 12, carbon 13, carbon 14. They all have the same atomic number because they're all carbon, so they've all got atomic number of 6 with 6 protons and 6 electrons. Their atomic mass is different though, 12, 13 and 14, which means their number of neutrons is different. So 12 minus 6 gives you 6 neutrons in carbon 12, 13 minus 6 is 7 neutrons in carbon 13, and 14 minus 6 is 8 neutrons in carbon 14. Some isotopes of some elements are unstable, which means they contain too much energy and they will decay, giving off ionizing radiation as they do. Ionizing radiation is radiation produced by the decay of the nuclei of unstable atoms, and there are several types: alpha, beta minus, beta plus, neutron and gamma radiation. You can see some of that radiation happening here in this diagram, and what you'll see is the radiation is produced from the nucleus of an atom, not from the electron shells. So alpha radiation is made of alpha particles, which are 2 protons and 2 neutrons. It reduces the atomic number by 2 and the atomic mass by 4. It has high ionizing power and low penetrating power. Beta minus radiation is made of fast moving electrons. It increases the atomic number by 1, does not affect the atomic mass. It has medium ionizing power and medium penetrating power. Beta plus radiation is made of positrons. It makes the atomic number go down by 1. It has no change on the atomic mass, has medium ionizing power, medium penetrating power. Gamma radiation is very high frequency electromagnetic radiation, so it does not change the atomic number, does not change the atomic mass. It has low ionizing power but very high penetrating power. It can be stopped only by lead or thick concrete. And finally, neutron radiation is a neutron. It does not change the atomic mass but does reduce the atomic number by 1. Background radiation refers to the ionizing radiation that is naturally present in the environment, and it comes from a range of sources including radon gas, which bubbles up from radioactive rocks in the ground. It comes from buildings and from rocks in the ground. It comes from space, cosmic rays, and from our food and drink, and also from artificial sources, most of which are from medicine. We measure radiation using units of becquerel, so 1 becquerel is 1 decay per second, and we can measure it with a Geiger-Müller tube. Every time some radiation hits this, it gives a little click and it counts up the radiation there. If you wanted to measure the radioactivity of a sample, we would measure the radioactivity of that sample, but we have to take away the background radiation because the Geiger-Müller tube can't tell whether the radiation is coming from the sample or from the background. The half-life of a substance is the time it takes for half of the undecayed atoms in the sample to decay, and that is a fixed number for each isotope. The higher the half-life, the less radioactive something is, the shorter the half-life, the more radioactive it is. To find the half-life from a graph is super easy. You just pick a point on the y-axis of the graph, so 80 here, and we'll pick the point that is half of that, because we're talking about the time it takes for half of it to decay. Trace along and down, and in this case you can see it comes to 2 seconds, but it is different for every graph and for every different isotope you look at. Radiation can be dangerous in the short term. It can cause radiation sickness, which can kill very quickly. In the long term, it can cause DNA damage that leads to cancer. So in order to minimize the risks of that, you reduce the time you spend around the radioactive sources. You monitor your exposure using a special badge called a dosimeter. You wear protective clothing, and you work with shielding like this, and also you use long-handled equipment so you're not closely in contact. And finally, to remind you of the formulas you need to memorize for this test. So speed equals distance divided by time, acceleration equals change in speed divided by time, force equals mass times acceleration, momentum equals mass times velocity, force also equals change in momentum divided by time, stopping distance equals thinking distance plus braking distance, efficiency equals useful energy out divided by total energy in, kinetic energy equals half times mass times velocity squared. The change in gravitational potential energy equals mass times gravitational field strength times height change. and wave speed equals frequency times wavelength. Don't forget also to use success D, so star your target, underline the values, copy the values, convert the units, write out the equation, rearranging it if you need to, substitute your values, solve, and don't forget the units. Thank you for listening. The end.